Section 3.3, increasing and decreasing functions, the first derivative test. Derivatives can be used to classify relative extrema as relative maxima or relative minima. Increasing and decreasing functions on an interval, closed interval a to b, if a is less than b and f at a is less than f at b, then f is increasing on the interval. If f at a is greater than f at b, then f is decreasing on the interval. It could look like this. Now, function f could have done this. It could have done a lot of increasing and decreasing, but ultimately, if the starting point, f at a, has a lower y value, f at a, than the ending y value at the end of the interval b, then we say the function has increased over the interval, etc. Test for increasing and decreasing functions. If f is continuous on the closed interval a to b and differentiable on the open interval a to b, then if f prime of x is positive, the slopes are positive, f is increasing. If f prime of x is negative, our slopes are negative, then f is decreasing. If f prime of x equals 0, the slope is 0, then f is constant at that x value or at a relative maximum or minimum. To find intervals on which f of x is increasing or decreasing, first, locate the critical numbers on the open interval and use these to determine test intervals. So we're going to find where f prime of x is 0 or f prime of x is undefined and solve for x. This is a situation here where the derivative would be undefined. The function's continuous at x equals 1, but the derivative is undefined because the slopes from the left side of 1 have an abrupt change with respect to the slopes from the right side of 1. Determine the sign of f prime in each interval. So we're going to pick a value in the interval that is created by our critical numbers and determine if f prime is positive or negative. For instance, let's say I have a vertical asymptote. Let's say on this side, the first derivative is positive. We know that that means our function is increasing. Let's say that on this side, the first derivative is negative. We know that that function is decreasing. Number 3, determine whether f is increasing or decreasing, and that's determined by f prime positive or negative. Now, some vocabulary. A function is strictly monotonic if it is either increasing or decreasing on the entire interval. Here are some examples. If f of x is 3x plus 1, you recognize that as a line with a slope of 3. F of x is negative 2x. You recognize that is a line with a slope of negative 2. Tangent of x. Now, you know that tangent of x is always increasing except for the places where it's undefined. So on its domain, it is an increasing function. Cotangent on its domain is a decreasing function. X cubed looks something like this. Okay, x to the fifth, just a little bit flatter, okay, and so forth. So functions that are always increasing or always decreasing are said to be strictly monotonic. The first derivative test says if c is a critical number of f and f is continuous and differentiable on the open interval from a to b except possibly at c, then if f prime changes from negative to positive at c, then f of c is a relative minimum. In other words, f is going from decreasing to increasing behavior. If f prime changes from positive to negative at c, then f of c is a relative maximum. In other words, f is going from increasing to decreasing behavior. Example 1, find the relative extrema of f of x on this function 1/2 x minus cosine x on the interval. We know f is continuous because 1/2 x is a continuous function, cosine x is a continuous function, and in your properties of continuity, it said if you add or subtract continuous functions, you still have a continuous function. So now we're ready to find the derivative. So the derivative of this function is 1/2 minus negative sine x, which gives me 1/2 plus sine x. That is f prime. F prime is 0 when 1/2 plus sine of x equals 0. That's going to be when sine of x is -1/2. This puts our angle x in quadrants 3 or 4 because that is where sine has negative values, and where my y value is -1/2. We have the angles 7 pi over 6 or 11 pi over 6. Now notice we need to be in the interval from 0 to 3 pi, and these are. The next time around, here's 0, 1 pi, 2 pi, here is our 7 pi over 6, 11 pi over 6, and then 3 pi. So 0 to 3 pi, I can't go any more angles. Okay. So what this has done is this has created a division in the number line from 0 to 3 pi, where these are my critical numbers. This was where our function's derivative was 0. All right, so this now divides up these numbers. So we want to pick a nice number in the interval of 0 to 7 pi over 6. Wouldn't pi be a nice number to try? And from 7 pi over 6 to 11 pi over 6, wouldn't 3 pi over 2 be a really nice number to try? And then from 11 pi over 6 to 3 pi, why not 2 pi? Okay? And so what we're going to do is there are a couple of ways to look at this. You can look at this method. This is what's in the textbook. So notice that I have taken my interval from 0 to 7 pi over 6. At 7 pi over 6, my first derivative is 0. And then I have from 7 pi over 6 to 11 pi over 6. At 11 pi over 6, my first derivative is 0. And then I have 11 pi over 6 to 3 pi. And here are the values we decided we would test. And now we're just going to substitute that value in our first derivative. So the sine of pi is 0. 1/2 plus 0 is positive. So my first derivative is positive, so f is increasing. Now let's pick 3 pi over 2. Again, substituting it into our first derivative. The sine of 3 pi over 2 is -1 plus 1/2 is negative, so f is decreasing. First derivative negative, f decreasing. And then we tried the last one, 2 pi. The sine of 2 pi is 0. 1/2 plus 0 is positive, so f is increasing. So now we know the intervals over which f is increasing and decreasing. Now that we know f goes from increasing behavior on 0 to 7 pi over 6 and decreasing behavior from 7 pi over 6 to 11 pi over 6, that means we have a relative maximum when x is 7 pi over 6, where that derivative was 0, which means we have a horizontal tangent line. Likewise, when we move from 7 pi over 6 to 11 pi over 6, my derivative is negative, so we're decreasing. And at 11 pi over 6, my sign changes of my first derivative sign. So I go from negative first derivative to positive first derivative. So I go from decreasing to increasing behavior. So I've hit a relative minimum at that place where the tangent line has a slope of 0. Now, this is a way to set this chart up. Here is another way. Here's my number line from 0 to 3 pi, my 7 pi over 6, my 11 pi over 6. Notice I'm going to state f prime, okay, and here's what my f prime function is. Here's the numbers I tried. I wrote those real little, and I found f prime to be positive, so I concluded f was increasing, and I can up here with f draw an arrow that's going up. Then we had the first derivative negative, so we concluded f is decreasing, and I can draw that arrow down, and that's why at 7 pi over 6, I can see we have a relative maximum. And at 2 pi, we see our first derivative is positive, so f went from negative to positive, decreasing to increasing, so we have a relative minimum, and you can see a general shape of the graph. All of the rest of the examples are going to follow the same process. It's just going to look a little bit different because the functions get more complicated. Okay, so we're going to determine the behavior of f of x equals x squared minus 1 to the 4/5. Once again, find the derivative and clean it up. Look at how much cleanup had to happen. This is going to come down below. 4 times 2 is 8x. And we can factor our difference of 2 squares. Now we have an issue that we have to consider. When the first derivative is 0, that's easy. But our first derivative is undefined when x is 1, but the function itself is defined there, so we definitely have to look at that. So that's another critical number. So our critical numbers are at x equals 0 and at positive and negative 1, where the first derivative is undefined. Again, If I want to look at a chart, notice that the numbers 0 and positive and negative 1, we're just going to go in order. Negative 1 was the first derivative was undefined. 0 was where it is, the first derivative is 0, and x equals 1 is another place where the first derivative is undefined. So these numbers divide our number line from negative infinity to negative 1, open interval, then from negative 1 to 0, and 0 to 1, and 1 to infinity. And we're going to test a value in all of these. It doesn't matter what you test. I picked negative 10 here, I picked negative 1/2 here, 1/2 here, and 5 here. I'm not interested in so much what the number is as to whether I'm positive or negative when I test it. So for instance, when I take negative 10 and I substitute it here, the top is going to be negative. The bottom, I have a negative plus 1. Negative 10 plus 1 is negative. Negative 10 minus 1 is negative. I have 5 over the 5th root of positive. So this is a negative over positive, which is negative. See, I'm not really worried about the actual value of the number. I'm worried about the sign. So let's look at negative 1/2. Again, the numerator is going to be negative. The denominator, negative 1/2, makes this factor positive, makes this factor negative. So I have the 5th root of a negative quantity, which is negative, times that positive is negative. And a negative over negative is positive. 1/2, the numerator is going to be positive. The denominator is positive, negative, negative. Positive times negative is negative. So a positive divided by negative gives me my first derivative negative. And again, 5, that's going to be positive on top. 5 times positive, positive, 5th root of positive is positive. Positive over positive is positive. That's a lot of positives. Okay? First derivative negative, f decreasing. First derivative positive, f increasing. First derivative negative, f decreasing. First derivative positive, f increasing. Now, we know our function is continuous at these two values for which the first derivative was undefined. So I have a cusp at those two places, a sharp point. Okay, and we've got a relative minimum here because I went from decreasing to increasing behavior. We have a relative maximum at x equals 0, and we have a relative minimum again at our cusp x equals 1. This is the other way to set it up. Notice this time I have arrows on the end of my number line. The last time it was from 0 to 3, so I did not have arrows, but this indicates all of the numbers. Again, you must label this to show what you're finding. F prime, what is f doing? What is f doing? Okay, so f prime was negative in this interval. Notice, by the way, I'm not putting the numbers I'm trying on the number line. That makes it very, very confusing. You either want to have those in your head, just think about it, but don't write those numbers up here. Only the numbers that are your critical numbers, or in the future, a vertical asymptote will also go on this graph. But anyway, there's the same information written a little differently. You might want to pause the video and write this down if you like this layout. Notice we can talk about f is increasing on the interval from negative 1 to 0 and 1 to infinity. F is decreasing from negative infinity to negative 1 and 0 to 1. Our final example happens here. You will notice the function is not going to be defined at x equals 0. I have a 0 in the denominator, so I already have a place I need to think about. There's several ways to simplify this. I just chose to write it like this, and here's my function. I have not taken derivative yet. We are now ready to take the derivative. That should be a piece of cake. This becomes this, which becomes this. Now, when is this 0? This will be 0 when x cubed minus 1 is 0. Let's remember, this is a difference of cubes. It factors like this. The cube root, x, same sign, minus cube root of 1. And then square this term, change the sign, multiply these, you do not double, and change the sign. Most of the time, this is not going to factor. It depends on what this function actually looks like. So x equals 1 is going to be where this is 0. The denominator is 0 when x squared is 0. That's at x equals 0, but let's remember the function itself is not defined there, so our vertical asymptote must go on the chart as well. So we have, when x is 0, this is a vertical asymptote. When x equals 1, we don't know if it's a relative max or min yet. We have to do our analysis. So we're going to pick a number smaller than 0. I picked -5. Go here, substitute -5 in. -5 cubed is really big. -1 is negative. Times 2, so the top is going to be negative. The bottom is going to be -5 squared, positive, so that makes this negative, f decreasing. Picking a number between 0 and 1, 1/2. 1/2 cubed is 1/8. -1 is negative. Numerator is negative. Denominator is positive, and so the first derivative is negative. And now picking a number bigger than 1, I picked 3, you could pick anything. That's positive, times 2 is positive, divided by positive is positive. So we have f decreasing here, then we have a vertical asymptote, and then we have f decreasing again. And then we have a relative minimum, and f is increasing because we are continuous when x is 1. Again, here it is if you want to see it in the other layout. Notice vertical asymptote goes on the number line, and 1. We knew this was where the first derivative was undefined, so is the function. This was where first derivative was 0, and this is what our analysis is going to look like. And your TPs for section 3.3 are 5, 7, 11, and 17. See you next time.